All right, we are going to finish section 1.3 by talking about increasing, decreasing, and constant functions, and also local and absolute maxima and minima. So we'll start with increasing, decreasing, and constant functions. So of course we can think about functions from left to right? We usually go from the negative to the positive x-axis. So we can think as if we're walking up a hill on this function and then down a hill and then up a hill, right? So the function is increasing when we're walking up a hill. Okay, so the function is increasing as we go from left to right here. And the way that we express that is as an interval. Okay, so we could say, where is the function increasing? Well, it's increasing on this interval here, all the way from forever up until it looks like -2 on the x-axis, right? All the way from negative infinity up to -2, the function is increasing. And then, as we move along the axis here, we're decreasing along this interval here from -2 to 2 on the x-axis, right? So the interval we're looking at is along the x-axis. And then it's increasing again from 2 up to infinity, okay? So this is the function that's graphed there. And these are the intervals where the function is increasing, right? From negative infinity to -2, union, right? Remember this line from a section ago. And then from 2 to infinity, okay? And it's decreasing, we write it as from -2 to 2. And notice that for these intervals, we use just regular parentheses, not square brackets, because at those points, the function isn't increasing or decreasing, right? So the intervals don't include those points on the graph, okay? So something else we can talk about on this graph are the local maximum and the local minimum, okay? So as we're walking, the function is increasing and it changes to decreasing, right? And here at the top of the hill is a local maximum. And we say it's a local maximum because if we just looked at part of the graph, it would be the biggest, it would be the maximum y value, okay? But if we look way over here, there's going to be some y values that are bigger, right? And that's fine. We're just talking about in this little area, we have a local maximum, and it happens at a point, right? The point it happens at is -216. And we have a similar thing here with a local minimum. There might be a number, there's a value over here that's less than -16, but we're just looking at it locally, just this one part of the graph, right? So local minimum happen when the function goes from decreasing, changes to increasing. So the local minimum happens at the point to -16. So we'd say that the local minimum is -16, and it occurs at x equals 2. Okay, so it occurs at an x value. And if they ask what is the local minimum, it's the y value, right? And similarly for the local maximum. Okay, so here's just another illustration. They happen, like a local maximum happens when it goes from increasing to decreasing. Okay, and that point there, the f of b is the local maximum value, and it happens at the point x equals b. So why don't you just take a minute, and sometimes there's more than one. Take a minute and say what you think these the local maximum and local minimum are for this function. Pause the video and write that down, and then we'll do it together. Okay, so first let's do local minimum. So let's talk about the intervals that this function is increasing and decreasing on. Looks like it's decreasing from negative infinity all the way to -1. Then it's increasing, sorry, not -1, 1. The interval would be from negative infinity to 1. The y value is -1. Don't get tripped up like I just did. Then it's increasing from 1 to 3, right, along the x-axis, decreasing again from 3 to 4, and then increasing from 4 to infinity. Okay, so the local minimum, and there's actually two of them. The local minima, that's the plural of minimum. The local minima happen at this point, at 1, -1, and at this point for, it's like 0.6 or something. Okay, those are the two local minima. And the local maximum, there's just one. It's going to happen here at 3, 1. Okay. So here's the official definitions of local minima and maxima. It's good to just practice. You won't ever have to rehearse this definition for me like on a test, but it's good to practice learning how these definitions are stated. So function f is an increasing function on an open interval if f of b is greater than f of a for every two input values a and b in the interval where b is greater than a. Okay. And decreasing is similar. So you might want to pause the video and think a little bit what that means. Okay, if this is if there's an interval around a point and the y value is greater at the point b, the output value of f of b is greater than the output value for any other a in that interval, you've got a local maximum. Sorry, I'm speaking incorrectly. This is not a local maximum. This is an increasing function, okay? If the output value is greater than the output value for any point, as long as b is greater than a, right? So if you're moving along the x-axis, if you have a point b that's greater than a, so it's farther to the right, if the output value is greater than this, the function is increasing there. And similarly for decreasing. And here we've got the local maximum. Sorry, I was looking at one thing and speaking another. So here, the definition of a local maximum. Okay, so if the output value for b is greater than the output value for any number that's in an interval, you've got a local maximum, and correspondingly for a local minimum. You might want to just pause the video and think about those definitions for just a minute, see if they make sense to you. All right, so again, where is this function increasing? Where is it decreasing? Where are the local maximum minimum? So it's decreasing from negative infinity to negative 1, increasing from negative 1 to 1, decreasing from 1 to infinity. Local minimum is at 1, negative 2. It happens at the point x equals negative 1, and the local minimum is negative 2. Local maxima happens here at 1, 2. It happens at the point x equals 1 and has a value of 2. So let's think about the toolkit functions. Okay, we're going to keep referring to these the whole semester. A constant function is neither decreasing nor decreasing, so we just say it's constant. An identity function, right? This line here, it's increasing everywhere. Quadratic, it's decreasing. We're talking about just the toolkit function, the regular x squared function, right? It's decreasing from negative infinity to 0, increasing from 0 to infinity, and has a local minimum at x equals 0. The x cubed function, a cubic, it's increasing everywhere, right? It's always getting bigger from left to right. The reciprocal function, this one's a little bit trickier. Let's see, it's decreasing from negative infinity to 0. And then it's also decreasing from 0 to infinity. The only place it's not decreasing is at 0. So we write that using interval notation as negative infinity to 0, union 0 to infinity. How about the reciprocal squared? Well, let's see, from negative infinity to infinity, it's increasing. And then from negative infinity to 0, it's increasing. From 0 to infinity, it's decreasing. Okay. Cube root, it's increasing everywhere. Square root, it's increasing everywhere that it exists, right? So that would be from 0 to infinity and 0 with just a regular parenthesis. Absolute value, let's see, it's decreasing from negative infinity to 0. And then from 0 to infinity, it is increasing. At 0, it's neither, right? There we have a minimum value, a local minimum value. Okay, well, we've been talking about local minimum and local maximum values. What about absolute maximum and minimum values? Okay, so here we've got a function that's just defined on just from negative 1 to 2, right? So it's just a restricted domain and range. So we could say, well, here we've got a local minimum, right? But it's also the actual lowest minimum value of the whole function, right? So not only is it a local minimum, that is the minimum value. That is the absolute minimum of this function. It happens at f of 0, and the value is negative 2. How about what is the absolute maximum value of this function? Well, the highest it ever gets in the y-axis is here at 2, and it happens at this point, at 2 of 2, at 2, right? X is 2, Y is 2. So that's the absolute maximum value. So we can define that the absolute maximum of f at x equals c is f of c, right? So the value of the function at c, where f of c is greater or equal to f of x for all the x in the domain. And the absolute minimum could happen at a point x equals d, and the value would be f of d, where f of d is less than or equal to f of x for all x in the domain of f. So again, I'd encourage you just to pause and think about that definition for a minute. I know with the notation, we're using function notation and lots of kind of symbols. Getting used to these definitions is an important math skill you're going to learn this semester. So just take a minute and think about what it's saying. All right, so we've got one last example to look at here. Let's find local minima and local maxima for this graph. So let's see, here we've got a local minimum, right? It happens at 0, 0, because the function changes from decreasing to increasing. But what's the absolute minimum value? It's going to happen here at 3, negative 10. Right? So the absolute minimum is this point, and the absolute minimum value is negative 10, but we do have a local minimum here. Here we've got a local max, right? Because it changes from increasing to decreasing, increasing to decreasing. And what looks like at negative 216 and at 216. But what's the greatest value this function ever reaches on the y-axis? It's 16. So these two values are also the absolute maximum values. So sometimes you can have two absolute maximum values, right? The absolute value is 16. Sorry, the absolute maximum value is 16. And that occurs at x equals 2 and at x equals negative 2. All right, so that is the end of section 1.3. Let me know if you have any questions about these things, these increasing and decreasing intervals, or absolute or relative maximum or minimum values.